Okay, so in the previous video we saw the production of this equation where work is equal to the sum of the forces applied over an incremental distance. So imagine that you're trying to move an object. You have to force it to move. And every piece of distance that you have, if you sum all those pieces, you have to apply a force for every piece. You add that up and that's the total work that you do to move an object. We know from Newton's second law that force is mass times acceleration. So F equals ma is Newton's famous second law. Force is mass times acceleration. And we know that acceleration is the change in velocity per the change in time. Acceleration is the rate of change of velocity, or the change in velocity per change in time. So we're going to replace this F with this F, which is equal to this M and this A. So we've got work is the sum of the force, but the force is mass times acceleration, and acceleration is dv by dt. And then finally I have a dx. We're now going to exchange these two products. dv multiplied by dx is the same as dx multiplied by dv. So we can write work is the sum of mass times by the change in position multiplied by the change in velocity divided by the change in time. So again, we've just exchanged these two. And we notice now that dx over dt, this is the change in position per change in time. Well, the change in position per change in time is just velocity. So we can rewrite this as work is the sum of mass. This whole thing now becomes velocity, and then we have change in velocity. Sums only apply to things that change. So here the sum ignores the mass. It could ignore the velocity, but it's going to hit this change in velocity here. Now, although the velocity here does not have a d, I can't ignore it because the thing that does have a d is velocity. So because the sum attacks the d, and the d contains a velocity, the sum is going to impact this velocity. However, the sum is not going to do anything to mass. And typically, a mathematician or a scientist would move anything that the sum won't affect to the left side of the sum. So we'd rewrite this as work is the mass, get the mass out of the way, and then the sum is left to hit velocity because it's trying to attack the d, and the d contains velocity. So this is as far as we can go without explaining a quick rule. So the following rule is a fundamental rule of integral calculus. If you take the sum of any variable raised to a power and then change it with the variable, then this fundamental rule says that this is equal to the variable to the power n plus 1 divided by n plus 1. So this is a rule that we're now going to have to use. So the sum of any variable x raised to the power n as the variable x itself changes is equal to the variable x to the power n plus 1 divided by n plus 1. We notice here that v is to the power 1. So this is m sum v to the first power dv. If we apply this rule now, work is mass. And then we have v to the 1. So that's v to the 1 plus 1, which is v to the 2, divided by 1 plus 1, which is 2. So we have work is mass times velocity squared over the number 2. Now this is equal to kinetic energy. Which I'll typically write KE. So now we've used work to understand kinetic energy, mv squared over 2. I would expect that you know this equation. This is definitely going to be useful moving forward in chemistry. And you may or may not know that kinetic energy is the energy of motion. You can see it in the equation. We've got an object with a mass that's moving with a velocity. So anything that moves has kinetic energy. And this is the origin of kinetic energy.